Okay, so today's topic is electromagnetic waves, right? So already about electromagnetic waves, I think it's not a new topic for you. So we know we completed electrostatics and we completed magnetism. So all the topics what we discussed, so we will bring into um, the one set all the formulas, and one new concept is introduced, which is nothing but displacement current. So all the things will be coming together in electromagnetic waves. Okay, so what we studied earlier we'll see it later. So now one topic which is uh, introduced here is nothing but displacement current. So later on we will relate all the things, but before relating we'll see about a new concept here which is introduced, which is nothing but displacement current. Okay, so what do you mean by displacement current? So one day Maxwell, what he did is, this is the Maxwell observation, so we can write here as Maxwell is a scientist. He observed the thing. Okay. Maxwell's observation. So what he observed, and we'll discuss now, and he gave a new concept which is the displacement current. So what he did actually, we'll discuss now. So he considered a capacitor. Okay. So he considered an uncharged capacitor to a battery. We'll try to relate everything. It takes some time. Okay. So he considered a capacitor, and that capacitor is connected to a battery. Okay. So what will happen? We studied in the electrostatics. So definitely charges with respect to time, it will store on the plates. Right. Slowly the charge increases in the plates. So charge increases, what will happen? Electric field increases. We studied all these things. We'll move it quickly. Okay. So now if charge increases, electric field, what will happen? That will increase. So now what Maxwell observed here, concentrate. So he considered a magnetic needle. Let us assume he considered a magnetic needle, and he placed nearer to this conductor. Let us suppose it is a magnetic needle. Right. So north and south, we studied all these things in magnetism. He related all the things with. That is the important thing. Okay. So uh, nearby that conductor, he placed a magnetic needle. What will happen? So current started flowing here. So definitely magnetic needle deflects. So this needle definitely it deflects. We know. Okay, very good. He got the same, and we know that. Some of the current which comes out from the other plate and it is reaching to the battery, and he placed a needle here also, right? And he placed the needle there also. Now what will happen is, here also the magnetic needle, what happens? It deflects. So that also we studied in magnetism. So here he placed, and that is deflected, and here he placed, that is also deflected. Now the interesting thing what he observed is, he placed he placed that magnetic needle he placed that magnetic needle in between the capacitor. In between the plates of the capacitor, he placed the magnetic needle. So what will happen actually? According to our concepts, what we studied till now, so we can tell, Array sir, there is no current between the plates. If there is no current between the plates, so no magnetic field will be generated. So therefore, the deflection in the magnetic needle will be zero. So, but what happened is, what Maxwell observed is, the deflection takes place. So the magnetic needle deflects all of a sudden. What Maxwell observed is, so in these two places we know that it will deflect. So it is deflected, but in between these two plates, if a magnetic needle is placed, and we know that there is no current, no magnetic field, it won't deflect. But what happened is, it deflected. It is deflected. So why it is deflected and all the reasons given by the Maxwell. Got the point? So why it is deflected and what is the reason behind that? So it is because of the conventional current or because of any extra current which is included and what we have to do with that. So all the things we have to study now. So definitely the observation is the magnetic needle is deflected. All right. So how it is deflected, we'll see now. All right. In EMI, we studied a point. So try to relate all the concepts now. In electromagnetic induction, we studied a point. So what is that? Anyone? Try to recall. In electromagnetic induction, we studied a concept called induced electric field. So try to recall that concept. So what do you mean by that induced electric field? So now, if a change in the magnetic field is there, if change in magnetic field, what happened? If there is a change in the magnetic field in any region, in any area, so what will happen there is definitely change in the magnetic field. If it is there in any area, so what will happen there is electric field will be induced. What will be induced? Make that point clear. If change in the magnetic field is there in any area, in any region, at that particular region, electric field will be induced. So this concept, I think, we studied. Electric field is induced. Electric field is induced. Yes or no? So change in the field, at that point, if you place any charged particle, definitely it moves. The concept of induced electric field. The charged particle, definitely it moves. So magnetic field, it won't give the kinetic energy to the particles. Then how the charged particle is moved initially? That is because of what? Electric field developed in that region. So we have a formula there, I think. So the formula is integral E vector dot dl vector, which is equals to the change in the flux. So we can write it as d phi by dt. If you remember the concept, so the formula also we have written there. Okay. So integral E vector dot dl vector equals to minus d phi by dt. That we studied in EMI. Now the story according to the previous experiment what we did, that is in electromagnetic waves. Now the story is, now the concept is, so now what is happening between the plates? By try to recall the thing. What is happening between the plates? If time increases, the charge what it is stored inside, it is increasing. Got the point? If time increases with respect to time, what is happening is charge, how much it is stored inside the plates, that is increasing. So if charge which is increasing, then we can tell electric field also increasing. In the sense, the change in the electric field is taking place at that point. So change in the electric field is taking place at that point. So now the reverse concept of this you have to apply. What is that? Think. So change in the magnetic field which leads to the electric field. Now the concept is change in the magnetic field, so change in the electric field which leads to magnetic field. That is the concept. Okay. So the finally Maxwell, what he concluded is, in a particular region, if electric field changes, their magnetic field will be developed. If magnetic field changes, their electric field will be developed. So in the nature, electric and magnetic fields will be together. As a concepts, we have separated that and we studied. But wherever the change in one concept is there, there automatically another concept will be induced. So he finally concluded that so change in the magnetic field, which change in the electric field, which results the magnetic field between the plates, and if you place the magnetic needle, definitely that needle deflects. So this is the Maxwell's observation. Okay. So now you'll get more doubts. Why? Because our magnetic needle deflected. So in the sense, indirectly we can tell some amount of the current will be induced at this point. So how much amount of the current will be induced and all, we will calculate. All right. So now we'll try to calculate some equations based on the Maxwell's observation. So start between the plates. What will be the electric field by? Come on. We'll start calculating the equations. Between the plates, we can write the electric field equals to sigma by epsilon naught. We know the electric field between the two plates, which is sigma by epsilon naught. We know that. So if we continue, what will be the charge stored, or charge density formula also we know, that is nothing but charge per unit area. So sigma, which is equals to charge per unit area. So replace with sigma. So how much charge is being stored? Let us assume it as plus q and minus q, but that should be constant or that should be variable by. That should be variable. So E equals to sigma by epsilon naught, where sigma is q by a times of epsilon naught, we can write. Alright. So now, if you write the next equation, EA epsilon naught, which is equals to q. So what is this E times of A? From electrostatics. So E times of A, which is nothing but electric flux, we can write. So therefore, we can write it as electric flux times of epsilon naught, which is equals to Q. Electric flux times of epsilon naught, which is equals to Q. Right? So now charge is constant or charge is variable here. So charge is variable here. So therefore, what we have to do? You have to differentiate. Yes or no? Variable things we need with respect to time. So therefore, differentiate the above equation. Differentiate the above equation with respect to time. So time के साथ हम differentiate करना. So if you differentiate that with respect to time by, so what will get? So d by dt of electric flux times of epsilon naught, which is equals to dq by dt. So therefore, finally what we can write? What will be constant in this? Epsilon naught. So flux is changing by, if charge is changing, electric flux also will change. Number of field lines between the plates will change with respect to time, which is equals to dq by dt is nothing but current. So now what about this current? Is that normal conventional current from the battery or any current which is induced between the plates? So this current will be induced between the plates, and that current here we call as displacement current. So according to the Maxwell, he gave a new concept. If electric flux changes, their magnetic field will be developed. So directly magnetic field won't develop. So without any current. So the current which is developed at that point, we call it as displacement current according to the Maxwell. and the formula is epsilon naught d phi by dt. Okay, happy with that? So now final conclusion points of the Maxwell is remember Ampere's law, Maxwell's observations we'll try to discuss now. Okay, so integral B vector dot dl vector for a closed loop, which is equals to mu naught times of current I. So according to the Ampere's law, we studied this. According to the Ampere's law, we studied this. So now the Maxwell corrected this and he gave a proper result for this formula, which is mu naught I is exactly correct. After this much story, I think everyone understood. So another term also should be there, which is mu naught times of displacement current, and this is the current in the circuit, which is nothing but conventional current we can, or the current in the circuit, and this is the displacement current. So therefore, the final conclusion point is okay, integral b vector dot dl vector, which is mu naught times of IC plus mu naught times of ID. Again, we'll get it out. Sir, this mu naught times of ID you can apply everywhere or only between the capacitor? So only between the plates of the capacitor we have to use this ID concept, or anywhere we can apply? Answer please. We can apply everywhere. Anywhere we can apply. Anywhere we can apply. Not only between the plates. Here also we can apply by. But wherever electric field can change, if it is there, this concept we will get, and you have to apply that. So the final equation is replace this with epsilon naught d phi by dt. So this will be the final equation. Mu naught epsilon naught d phi by dt. Very, very, very important. In this topic, if question comes from NEET level or mains level, the chances will be more from this formula, which is mu naught epsilon naught and d phi by dt. So this is about the displacement current and what Maxwell observed. So if you open NCERT, so Maxwell equations will be there as a concept. Maxwell's equations. So in electrostatics and in magnetism everywhere, so Maxwell gave some equations. Okay, so we'll see all those equations now one by one. First equation I think we got from Ampere's law. He corrected it and he made it clear, which is mu naught times of IC plus ID, or mu naught times of IC plus mu naught times of epsilon naught times of d phi by dt. All right. So first formula I'm taking from there. It is already done. No need to waste much time. And Maxwell's equations. If they ask for board level, try to write the Maxwell equations. You have to write all these equations. So first one according to the Ampere's law, and the second one is Gauss law. Gauss law in electrostatics. I think that formula we know, which is no need to waste much time. So integral E vector dot dA vector, which is equals to charge inside by epsilon naught. Charge inside by epsilon naught. Next, third equation, what he gave is Gauss law again. Gauss equation, so Gauss law in magnetism. Gauss law in magnetism. What is the formula? Integral B vector dot dA vector, which is equals to 0. Got this point? We studied in magnetism in magnets. If you consider a magnet, magnetic field lines close from north to south outside, and inside it will be south to north. If any closed area, if we consider the number of field lines inside and the number of field lines outside, which is flowing through that particular area, will be same. So this integral B vector dot dA vector will be equals to 0. So now going to the fourth equation, Already we discussed that, I think. Anyone? In electromagnetic induction, so fourth equation is right. Already we discussed in electromagnetic induction. We have written a formula for induced electric field. So that induced electric field formula discussed, right? Change in the electric flux by or magnetic flux. Magnetic flux, right? So E vector dot dl vector equals to minus d phi by dt. And in some materials, the fifth option or the fifth formula is also included, which is the Lorentz force. So Lorentz force, which is nothing but net force, which is equals to electrostatic force plus magnetic force. Electrostatic force plus magnetic force. So Maxwell observations, wherever magnetic field and electric field combination concepts are there, everywhere Maxwell observed some equations and all the results we discussed now. So wherever combination of electric and magnetic fields are there, their Maxwell contribution is more. Okay. So finally, after knowing all these results according to the board level or everywhere, so these equations, if they give, we have to answer. So one more thing here, important story is about displacement current, and the formula is that clear. So in this topic, the main important part is the displacement current. Then after that, some properties we have to discuss. We'll see those characteristics. Characteristics of electromagnetic waves. Now, whatever we discussed in 11th and in 12th, all the waves stories, all the electric fields and magnetic fields, all the things, we will try to recall the things. Okay. So, characteristics of electromagnetic waves. So, now, electromagnetic wave. Arabic basic concept, electromagnetic wave, which is nothing but light. So that electromagnetic wave, which comes under mechanical or non-mechanical waves. What type of waves is that? So mechanical waves requires medium, and non-mechanical waves doesn't requires any medium. Right? So now electromagnetic waves, which is nothing but non-mechanical waves. Electromagnetic waves. We know all these things. Just try to quickly recall the things. It is a non-mechanical, and as well as we call it as transverse waves. We know that we studied in 11, right? And we studied in wave optics. Transverse waves, electromagnetic waves comes under non-mechanical and as well as transverse waves. And the next point, if we go in electromagnetic waves, how many waves are inbuilt there? So we can take electric field as a wave, and we can consider magnetic field as another wave. So these two transverse waves, if we combine these two transverse waves, if we combine, then the result what we will get is the electromagnetic waves. So how we have to combine these two waves? How we have to combine? I think we know from the lower classes we studied a formula which is nothing but electric field vector cross magnetic field vector, E cross B. What is this? We cannot. Very important. E cross B. The direction of propagation of the light given by this equation. The direction of propagation. So some materials they write it as S vector, pointing vector, not exactly equals to. If you write proportional, I think will be better. So S vector proportional to E vector cross B vector. So if you remove proportional, you will get a constant. We'll discuss about that. So E vector cross B vector. What is S vector? propagation of the wave. So it gives you the direction of propagation of the wave. S vector gives you the direction of the propagation of the wave. E vector cross B vector. So how we have to relate these two? So from the lower classes we are studying that. So electric field and magnetic field, if they are perpendicular to each other, then the perpendicular to both electric and magnetic fields, the light will propagate. Yes, sir? So if the propagation is along, let us suppose x-axis, I am considering it as y and it as z. So now electric field I am considering, let us suppose, along y-axis, right? And the magnetic field, if I consider along z-axis, magnetic field, if I consider along z-axis, happy with that? Amplitude should be same. Don't worry about that. Here it is same. Here I think it is little lengthy. Very good. One more minute. Okay. So little bigger. Try to adjust. Okay. So electric field is along y-axis I consider, and the magnetic field is along z-axis. So try to apply that E vector cross B vector. How much it will be? Come on. E vector cross B vector. E vector cross B vector. So propagation which gives you with your thumb. So this is the propagation direction, and this will be the electric field direction, and this will be the magnetic field direction. So it is proportional to S vector. So S vector, if I remove this proportional, we will get a constant which is 1 by mu naught times of E vector cross B vector. 1 by mu naught times of E vector cross B vector. And this X vector, actually we call it as pointing vector. Pointing vector. Pointing vector. Okay. So which doesn't mean, which means that S vector is nothing but it gives you the direction of propagation away. So if you write exactly with the proper relations, we'll get it as 1 by mu naught is the proportionality constant, which is multiplied with E cross B. So therefore, if you write with magnitudes, we'll write it as EB by mu naught. No worries. In some materials, they write it as EB by mu naught as equals to EB by mu naught. So magnitude wise, so with respect to direction, you can go with S vector equals to 1 by mu naught times of 1 by mu naught times of E vector across B vector. So the characteristics, the first one we are talking about the wave nature. Okay, so electric fields and magnetic fields, and we'll write electric field relation E vector which is equals to E naught sine. It depends. So I'll write it as kx minus omega t. Wave equation how to write? I think we know. Okay. So B vector which is equals to B naught sine. Again, it is kx minus omega t. So wave equations, sometimes they can ask. Previous recent mains level questions are there on this. They'll ask to calculate what will be the peak value of electric field and what will be the peak value of the magnetic field by giving some equations. So please don't overlook that. Try to revise it once. And next, moving forward to the next characteristic after the wave stories, anyone? Relation between a relation between the basic formula I think we all know: electric field, magnetic field, and speed of light. Electric field and magnetic field and the speed of light. Okay. So what will be the relation? I think we studied in velocity selector. V equals to E by B. V equals to E by B. So where V, according to this story, according to the electromagnetic waves or according to the photons, we call it as the speed of light. Where C equals to E by B, we can write. Okay. So the relation, if they give electric field, we can calculate magnetic field, or if they give magnetic field, we can calculate electric field. The relation we'll get from this, one of the important characteristics. And next, if they ask the speed of the light, if they ask the speed of the light in different mediums, speed of light is nothing but speed of electromagnetic waves, right? The speed of electromagnetic waves in different mediums. If it is free space or vacuum, we can write it as C, which is equals to 1 by root over mu naught and epsilon naught. In vacuum or in free space, we can write C equals to 1 by root over mu naught times of epsilon naught. In any medium, if you want to calculate the speed of light in any medium, it is in any medium, we can write it as 1 by root over, it is mu naught mu r and epsilon naught and epsilon r. So in any medium, if we consider, it will be mu naught and relative permeability and relative permittivity. These concepts will come into consideration. So we know the relation is in any medium, which is nothing but in speed of light in vacuum or free space divided by, we can write it as mu r times of epsilon r. It is C by root over mu r and epsilon r. So relations we know. Yes or no? Try to revise it once. So C in any medium, speed of light in any medium, we can calculate. Next, after calculating the speed of light, next story is about, we'll talk about energy density first, then we'll talk about intensity. Okay, so we'll see about energy density. Energy density. Anyone? What do you mean by energy density? Try to answer the question. Energy density, call it as energy per unit volume. Okay, energy per unit volume, we call it as energy density. So I'll represent with rho, no worries. Okay, so energy per unit volume, which is nothing but energy density. All right. So now how many types of energy densities will be there? How many types of fields will be there? For all the things we have to write the equations. So first one we'll go with electric field. What will be energy density for electric field? Energy per unit volume for electric field if I consider. So energy density with respect to electric field. Already I think we studied, that is nothing but half epsilon naught times of E square. Can I write? So from where this formula came? I think we studied in capacitor. So energy, which is equals to half CV square. Energy stored in a capacitor, that is given by half CV square. Now proof if you want we can write. So half. So instead of this capacitance, we know it as epsilon naught A by D times of V square. So instead of this V square, we can write, instead of this V square, now we can write it as What is the formula? E equals to V by D, where V is ED. So it will be E square and D square. One D will be cancelled. So where A and D is nothing but volume. So replace E and D with volume. So energy density per unit volume not E square. Just have proved for your convenience. Try to recall the formulas. Half epsilon naught E square will be the energy density in terms of electric field. In the similar way, make it as one. In the similar way, we can calculate energy density, energy per unit volume with respect to magnetic field. So it is energy density with respect to magnetic field, and the formula will be directly. So the formula is B square by 2 times of mu. B square by 2 times of mu. A small calculation part. Come on, start. So what is energy stored in the form of electric field in the sense that is half CV square we have written. Now in terms of magnetic field, if you want to write the energy, we have to go for electromagnetic induction, and we have a formula which is half Li square. So energy which is equals to half Li square. So now inductance formula, we already know that. What is inductance for a solenoid if I take better? So inductance for the formula is mu naught n square. Remember the solenoid formula with inductance for a solenoid mu naught n square pi r square times of L. Mu naught n square pi r square times of L, where pi r square is area of the solenoid, L is the length of the solenoid. So we can write by limiting that area and length with volume times of I square. So now if you, what we can write, multiply and divide with mu naught, multiply and divide with mu naught. Have I got that? Multiply and divide with mu naught. So what we'll get? U by V and V to the other side. So which is nothing but half. How much is that? Mu naught and mu naught will be mu naught square, n square and I square. Mu naught ni whole square, which is nothing but B square divided by what is left in the denominator by mu. So energy density formula is B square by 2 times of mu naught, and with respect to magnetic field and with respect to electric field it is half epsilon naught E square. Very important formulas in the energy of an electromagnetic wave. So now individually we calculated. Now we have to combine. So according to electromagnetic waves, if we combine these two fields, so we'll write the total or the net energy density, which is equals to energy density with respect to electric field and energy density with respect to magnetic field. So the next story, energy density with respect to electric and magnetic fields. So what is the energy density formula by? So we have written it is half epsilon naught E square plus half B square by mu naught. So we know the relation between E and B. So we can write it as V equals to E by B. So where V is nothing but speed of light, where E which is equals to C times of V. V equals to C times of B. You can eliminate either electric field or magnetic field. So I have written E equals to CB. So I'm trying to eliminate electric field. So half times of epsilon naught E square. How much will be that? It is C square times of B square. So now half times of epsilon naught, instead of C square, we can write it as 1 by root over mu naught and epsilon naught whole square. So it will be mu naught times of epsilon naught times of B square in the numerator. Okay, so epsilon naught will be cancelled, and the other term will be same, which is b square by 2 times of mu naught plus again b square by 2 times of mu naught. So finally, it is b square by 2 mu naught. Have I observed both the things we got same or different? So in the sense, energy density, which is the final conclusion with respect to electric field and with respect to magnetic field, both the values we can conclude it as same. Alright? So b square by 2 mu naught and b square by 2 mu naught. Or if you want to eliminate this magnetic field, again at the end we'll get half epsilon naught and what? E square here. So you'll get it as b square by how much by mu naught we can write, or in terms of electric field if you write that half won't be there, it will be epsilon naught times of E square. So in terms of magnetic field or in terms of electric field, we can write directly, both will be the same. So it is energy density. Net energy density, if we consider, we can take it as b square by mu naught and epsilon naught times of E square. Okay, but if it is constant values, if they give in the question, then you have to apply these values. If wave equations, if they give, then we'll go for the next point. Have we got the point? Half epsilon naught E square, I didn't consider the complete wave equation. Okay, so E, if it is constant, and B, if it is a constant value, then we can go with this b square by mu naught or epsilon naught times of E square. Now, if a wave equation is given in the question, let us assume a wave equation is given in the question. Let us assume E naught, E equals to E naught sine, how much? Initially we have written kx minus omega t, and B equals to B naught sine kx minus omega t. We write like this. Then how to calculate? Some. So previously a constant value I considered. For that, how to calculate I have shown. Now we are discussing the electromagnetic wave. So definitely if they give the wave equation like this, then how to calculate? So check. So net density, which is equals to energy density with respect to electric field and energy density with respect to magnetic field. Try to substitute the values. So it will be half epsilon naught. In terms of E square, you can substitute this. That will be E naught square sine square kx minus omega t, and again plus how much? The formula is b square by 2 mu naught, which means 1 by 2 times of mu naught b square, which is nothing but b naught square sine square kx minus omega t. So sine square kx minus omega t. If a wave equation is given in the question, you have to replace with the wave things. If a constant is given, that story will be different. So now, which is equals to, now start how to calculate. It is half epsilon naught and a naught square. It depends again. So in the question, if they ask to calculate average energy density, if they ask instants at x equals to 0, at t equals to 0, then we can place there. Or else, so generally if they ask for the complete wave, so we can go with average energy density for that wave. Got that? So average energy density. What is average wave? So sine square function, if it is there in any concept. So what is the average of sine square function? Or I think some authors they will write the wave equation. No? We can write in terms of sine. We can write in terms of cos. So cos square or sine square. So whatever it might be, if you are going for average, that average of sine square or cos square function will be 1 by 2. Okay. So the average of sine square cos square values will be 1 by 2. So you can replace for average at an instant, in the sense they'll particularly mention at what distance at what time. But here average I considered. So for average sine square value you can replace with 1 by 2. So finally you can write it as another 1 by 2 in the equation plus b square by 2 times of mu naught with another 1 by 2. So therefore average density, finally we can write it as 1 by 4 epsilon naught e square plus 1 by 4 b square by 2 mu naught. But we know a point, another 2 will be there. No, I think some. Okay. So it will be 1 by 4 epsilon naught e square and 1 by 4 b square by mu. So already we know that b square by 2 epsilon naught and half epsilon naught e square will be same. So you can add directly to get the equation. Have I got this point? Already we proved that half epsilon naught e square. Yes or no? What we proved? Half epsilon naught e square, which is equals to b square by 2 times of mu naught. Yes or no? So finally, if you want another equation, so average density which is equals to what we can write, instead of half epsilon naught b square, so we can write b square by 2 epsilon naught. So here I am trying to change that. So instead of epsilon naught e square, I can write b square by mu naught. So it will be 1 by 4 if I take common. These two terms will be same. So it will be how much by? So 2 times of how much? 2 times of epsilon naught e square you can write, or 2 times of b square by mu naught you can write. Why? Because epsilon naught e square and b square by mu naught will be same. If we cancel, these two terms will be same. So now here this will be cancelled and the final relation will be average density, energy density, which is equals to epsilon naught e square by 2. Alright, got this? 1 by 4 times of, again these two things I took common and we got it as epsilon naught e square by 2. So if they give wave equation, average density we have to calculate net average density for both. Calculated net average density for both. So individually if they ask, you can go with 1 by 4 epsilon naught e square or 1 by 4 b square by mu. So this is the energy density concept. Okay, energy density, right? So after energy density, another important concept is about intensity. What is the relation between intensity and energy density, if I ask? Relation between intensity and energy density. Come on. Intensity, which is equals to general formula for intensity by, we can write power per unit area. We know that. So again, if you elaborate the things, it will be energy per unit area and unit time. Can we write like this? Anyway, all the things in waves we studied. In waves, power per unit area we studied and energy per unit area per unit time. We know that. Right? So what is my question? Intensity and energy density. So now what we can do? So energy per unit area and unit time. Energy density in the sense what way? Energy per unit volume. So to get volume, what I'm trying to do is I'm multiplying with I'm multiplying with length in the numerator and as well as in the denominator. Right? So multiply with length in the numerator and as well as in the denominator. Can I? So area times of length, which is nothing but volume. So energy per unit volume, we call it as energy density. Can I write? Yes or no? And length by time, which is nothing but speed. So speed of electromagnetic wave. Very, very, very important formula. I equals to energy density times of speed of light. So energy density formula we already discussed. Yes or no? So if they particularly consider the Pura wave, then we can consider I equals to net average density multiplied with C. Net average density multiplied with C. At this point or at any instant points in the question, particularly E value they have given without any wave stories, then no need to consider that average. That formula also we have seen, which is epsilon naught E square times of C. If average things, if it is there, and another half we'll get half epsilon naught E square times of C. So both formulas, if you remember, will be better. So the important one is average one only, I think. So it is half epsilon naught E square times of C. It is better. Or I equals to, we can write B square by 2 times of mu naught times of C. So the things will be same, right? So this is about intensity. Other stories are there on intensity. We'll see it next. So if you go for momentum and radiation pressure, final properties, final characteristics. Okay. So momentum, if you see how to calculate the momentum of an electromagnetic wave. So we can write E equals to mc square, right? E equals to mc square we can write. So now we can write E equals to, continue the things, mc times of C, where mass times of speed is nothing but momentum. So energy, which is equals to momentum times of speed of light. So if anyone asks about the momentum in any question, so we can apply momentum, which is equals to energy by speed of light. Got the point? Where P is not pressure by, don't be confused, that is momentum. So momentum, which is equals to energy by the speed of light. Energy by the speed of light. Finally, we'll go with, I think this concept also we studied in dual nature, I think. We call it as radiation pressure. Radiation pressure. So I won't go into the story why, because already you studied that, try to revise that radiation pressure in dual nature. So some points which is related into the electromagnetic fields, we'll discuss that. Okay. So radiation pressure. So what is the formula for radiation pressure? Right? Direct formulas, if I write, will be better. Whereas suppose if a photon which strikes, so that's why I said in dual nature we studied about the photons and the behavior of the photons and the characteristics. There you got all the things. I think if the photon strikes the surface, whereas suppose intensity is I, wavelength is lambda, and the speed of light is c, and the area that it strikes is a, and it is completely absorptive surface, reflective power is 0, absorptive power is 1 and reflective power is 0, then what will be the pressure if I ask? So to prove, I think it will be lengthy. So F equals to, you have to calculate the force. Before that, you have to calculate momentum. So momentum you have to calculate, right? And next, you have to go for force, average force, and then pressure. So directly I'm writing, if it is completely absorptive surface, after doing all those things, I think we'll get a famous formula, which is I by C. Completely absorptive surface, radiation pressure depends on intensity and the speed of light. Intensity of the light, intensity of the light, and the speed of the light P equals to I by C. If they ask force, I think you can calculate pressure, which is equals to force per unit area, which is equals to I by C, where force, which is nothing but I A by C. So this will be the force and this will be the pressure, not momentum. So pressure, which is equals to I by C, for absorptive power is 1 and the reflective power is 0. So the second case, if it is completely reflective, if it is completely reflective and absorptive power if it is 0. Absorptive power if it is 0, okay, and if it is completely reflective, then what will be the radiation pressure by? Come on. So here I by C, why? Because whatever the photons energy it got, so that is absorbed by the surface. Okay, so final momentum will be 0 and only initial momentum will be there. But here it is reflecting, so initial momentum also will be there and final momentum also will be there. So the change in the momentum is 2 times of h by lambda. If you try to solve, so 2 times. So everywhere you will get that extra 2 if you solve. So if P equals to I by C, here you will get it as 2I by C. Try to go through with the stories. Okay. So if you remember these two formulas, I think till mains level it is okay, right? So P equals to I by C and P equals to 2I by C. Area of the surface is A. So the photon which strikes the area perpendicularly, then only these two formulas will be acceptable. Or else another cos term, I think, or cos square term will be included in the story. Okay. All right. So this will be the radiation pressure and as well as force. Right? After these characteristics, after this characteristics, another very important concept is electromagnetic spectrum. Very important word. On the COVID batches, most of the questions in electromagnetic waves for mains and NEET given by this electromagnetic spectrum. Electromagnetic spectrum. Okay. So what do you mean by this? How many wavelengths will be there? All the wavelengths we have to consider. So try to write in the order. First one, radio, radio waves, microwaves, and next infrared. Next we'll go for visible, and in that visible also you have to write waves are in the reverse order. Make these points clear. Okay, waves visible and waves are in the reverse order. Next, ultraviolet, next X-rays, and finally it will be gamma rays. So finally it will be gamma rays. Now if you move from radio to gamma rays, if you move from radio to gamma rays, from radio, next micro, next infrared, visible. So if you go from radio to gamma rays, then what will happen is wavelength, what will happen? So wavelength increases or wavelength decreases? Wavelength decreases. In the order what I have given, their wavelength decreases. If wavelength decreases, what will happen? Frequency increases. If frequency increases, we know it as energy of that particular spectrum or particular wavelength, which is more. So wavelength decreases from here to there, in a sense from radio to gamma. So frequency increases, so energy increases. So now what you have to do is for all these what we call spectrum, for all these wavelengths, you have to calculate the ranges. For radio waves, for all these waves, you have to calculate the wavelength ranges and the uses. If you remember, definitely one question for sure. I think previously They ask the wavelength relation for different waves. Previous questions are there, last 1 or 2 years. You see wavelength relations, they ask more, and 1 or 2 questions you can see the frequency relations. So try to remember this story. If our time is not that much good, according to me, then they will ask what will be the uses, from where those rays generated, all those things they'll ask. So kindly go through NCRT ones. Those stories are clearly mentioned. So try to go through that point once. I have a small uh, PDF. Okay, so try to go through with that one. Try to open that. I think in any material, this type of the chat will be there. In CRT also the same story it is there. Sarma. So gamma rays. So you can see the frequency ranges. Yes, you can see the frequency ranges. Clear? You can see the frequency range and wavelength range, and from that particular gamma is generated. See, so if you go from radio waves to gamma rays, so what will happen? So the frequency range they give, and this is what is happening. So wavelength, according to your order, it is 10 to the power minus 3 to 5, and decreased, further decreased, so and so on. If you have to remember all these values, spend some time. So the chances will be there. We'll get some questions on this. Right? Thank you.